This is the screencast for section 8.4, example 6, integrands with infinite discontinuities. Alright, so say we've got this function that's got an infinite discontinuity. Well, we've got three scenarios that we could be trying to find. We could be trying to find from the infinite discontinuity to another higher upper limit of integration. We could be trying to find from a lower limit of integration to the infinite discontinuity, or we could be trying to find a lower and upper limit of integration with an infinite discontinuity in the middle. And we're going to use the same kind of strategy we did with infinite limits of integration. We're going to call that infinite discontinuity C, and let C approach the specific value we're looking for, either from the right or from the left, depending on which interval we want. So in this case, we'd let C equal A, or C approach A coming in from the right. In this case, we'd let C approach B coming in from the left. And in this case, we'd have to split it into two. So again, our strategy is going to be the same. We're going to first find the area from 1 to this variable. So from the limit we know to the infinite discontinuity, substituted in for a letter. And then we're going to find the limit of the area as A approaches that specific value, either from the left or the right, and then make our conclusion. So let's try one. Example 6 wants us to evaluate the antiderivative from 0 to 3. Well, I'm going to try and do this without a calculator. I know that there's going to be an infinite discontinuity here at 1. So I need to split up my integral into the antiderivative from 0 to 1 and the antiderivative then of the rest of it from 1 to 3. Since 1 is an infinite discontinuity, I'm first going to say, let's take the limit as C approaches 1, but from the left this time, because if I'm trying to find from 0 to 1, I want C to approach from numbers within that interval. So I'm going to approach from 1 from the left, so between 0 and 1, from 0 to C of our integrand dx. Then the other one's going to be the limit as C approaches still 1, but this time from the right, because now we want to integrate between 1 and 3, so we're coming in from the right, because between 1 and 3 our value is greater than 1. And then of our integral dx, integrand dx. So let's integrate. And fundamental theorem part 2 for both pieces. Now I'll simplify. The limit as C approaches 1 from the left, well, that's really going to be 0 to the 1/3, so that's 0. And this simplifies to be 3. Plus, this simplifies to be 3 cube root 2, 2 to the 1/3 power. And then as we plug in 1 over here, I get 0 again. So my total area under this curve between 0 and 3 is 3 plus 3 cube root 2 units. The now try problem number 25 says A, state why the integral is improper, and then evaluate the integral or state that it diverges. So part A, an improper integral could have an infinite upper or lower limit of integration. This does not. The reason why it's improper, this one, is because the integral has an infinite discontinuity at x equals 1. So that's within the interval of integration. So that means I'm going to have to split this integral. I'm going to take the limit as C approaches that 1, that infinite discontinuity, from the left between 0 and C, so the value is to the left of 1. And then I'm going to add the limit as C approaches 1 coming in from the right from C to 2, the values to the right of 1. Now, integrating that, that does not look like an inverse trig formula. If it was 1 plus x squared, it would be, but it's 1 minus x squared. I'm thinking integration by partial fractions. The denominator has 1 plus x, 1 minus x, so that means A times 1 plus x plus B times 1 minus x should equal 1. If x equals 1, A equals 1/2. If x equals -1, B also equals 1/2. So this first one, I'm going to be using partial fractions. So the limit of A over 1 minus x, which I know it should be 1/2 over, but I just put the 2 in the denominator where it belongs. And then plus B over 1 plus x dx. And I have the same thing as the limit as C approaches 1 from the right. Next, I'm going to integrate. So I have negative 1/2 the natural log of 1 minus x. It's negative because of that negative x in there. I'd have to divide by its derivative when taking the integral. And then plus 1/2 the natural log of the absolute value of 1 plus x. So in my next step, I'm going to factor out the 1/2 first, because I'm going to have the same thing here. I may as well do another step while I'm at it. So I have 1/2 factored out, and then 1 plus x is going to go in the numerator because that's the positive natural log, and then 1 minus x is going to go in the denominator because that's the negative natural log. Now, fundamental theorem of calculus part 2, plug in c, subtract plugging in 0. Same thing for this part. I'm just using this simplified expression here with the quotient inside the log. Now I'm going to do some simplifying. This left simplifies to 1/2 the natural log of 1 over 0 minus 1/2 times the natural log of 1. Uh-oh. And this is 1/2 natural log of 3 minus 1/2 natural log of 2 over 0. If we got 0 over 0, there may be something we could have done there because that sounds like a removable discontinuity, but this is not. Unfortunately, we did all of that work and this diverges. So we cannot find the area under this curve. Yeah, that's going to happen. You're going to go through all this work and then at the end figure out it diverges. Bummer.